You exist. I exist. The chair you're sitting on, the air you're breathing, the planet under your feet. It's all here. It's all made of stuff. We call that stuff matter. This seems obvious. So obvious it feels silly to even say it, but the fact that any of it exists is the single biggest mystery in all of physics. It's a cosmic crime scene where the main clue is our own existence. The problem starts with a simple, unsettling fact. For every particle of matter, there's a corresponding particle of antimatter. An electron has a negative charge. Its antiparticle, the positron, has a positive charge. A proton is positive. An antiproton is negative. Otherwise, they are identical. They have the same mass, the same spin. They are perfect mirror images of each other. You might think of antimatter as the evil twin from a movie, and in a way, it is. When a particle of matter meets its antimatter twin, they don't just cancel out. They annihilate, they vanish in a flash of pure energy, usually in the form of high-energy light or photons. Poof. Gone. This isn't just a theory. We make antimatter in labs every day. Particle accelerators like the Large Hadron Collider at CERN produce it constantly. PET scans in hospitals use positrons to create images inside your body. Antimatter is real. So here's the mystery. Our best understanding of the beginning of the universe, the Big Bang, tells us that energy should create matter and antimatter in equal amounts. It's a fundamental symmetry. For every quark that popped into existence, an antiquark should have popped into existence right alongside it. For every electron, a positron. A perfect balance. Think about what that means. In the first fraction of a second, the universe was an incredibly hot, dense soup of particles and antiparticles constantly being created and destroyed. As it expanded and cooled, these particles and antiparticles would have found each other. And they would have annihilated. If the balance was perfect, every single particle would have found its antiparticle partner. The entire universe of stuff would have wiped itself out, leaving behind nothing but a sea of leftover energy, a cosmos filled with light and not much else. There would be no galaxies, no stars, no planets, and certainly no people asking questions about why they exist. But that's not what happened. We are here, you are reading this. The universe around us is made, almost exclusively, of matter. We look out into space with our telescopes, and we see galaxies made of matter. We see stars made of matter. We see gas clouds made of matter. There are no signs of huge anti-galaxies annihilating with matter galaxies at their borders. If there were large pockets of antimatter out there, we'd see the constant flashes of gamma rays from the annihilation. But we don't. The universe is overwhelmingly made of one kind of stuff. Our kind of stuff. So the question isn't just, why is there matter? The real question is, why is there more matter than antimatter? Somehow, in the fiery chaos of the Big Bang, the perfect symmetry was broken. For every billion pairs of matter and antimatter particles that were created, something tipped the scales. For every billion antiquarks, there were 1,000,001,001 quarks. It was a tiny imbalance. A rounding error, really. But it was enough. After the great annihilation was over, after all the matched pairs wiped each other out, that 1 in a billion extra bit of matter was left over. That's us, that's everything. The planets, the stars, the great cosmic webs of galaxies stretching across the void. We are the leftovers, we are the cosmic crumbs from a feast where almost everything on the table was destroyed. This is the baryon asymmetry problem. Baryon is just the technical name for particles like protons and neutrons, the heavy particles that make up the nucleus of every atom. So it's the problem of why there are so many baryons and so few antibaryons. Solving it means understanding why we live in a universe of something instead of a universe of nothing. To figure out how this could have happened, we need a recipe. We need a set of conditions that could allow matter to win out over its twin. In the 1960s, the brilliant Russian physicist and dissident Andrei Sakharov thought about this problem. He wasn't even a cosmologist, but he saw the deep connection between particle physics and the universe's origin. He came up with 3 conditions, 3 things that absolutely must have been true in the early universe for us to be here today. If any one of them is missing, the puzzle doesn't work. The first condition is that you have to be able to break a fundamental rule. This rule is called baryon number conservation. It sounds complicated, but it's just a way of keeping count. You give a proton a baryon number of Plauen. An antiproton gets 1. A neutron gets Plauen. And an antineutron gets 1. Particles that aren't baryons, like electrons or photons, get a 0. The rule of baryon number conservation says that in any interaction, the total baryon number before and after must be the same. You can't just create or destroy baryons out of thin air. You can create a proton-antiproton pair from energy because the total baryon number is still 0 Plauen plus 1 is 0. but you can't just make a proton by itself. This rule seems to hold true in everything we see today. We've never seen a proton just disappear. If they did, the atoms in our own bodies would be unstable. But for matter to get a head start, this rule had to be breakable, at least for a little while in the extreme environment of the early universe. There had to be some process that could change the total number of baryons, turning non-baryons into baryons, or creating more of them than their anti-counterparts. Without this, you're stuck at a net count of 0 forever. Sakharov's second condition is the weirdest one. It's also the most crucial. The laws of physics themselves must have a tiny bit of bias. They can't be perfectly symmetrical when it comes to matter and antimatter. This is called CP-symmetry violation. Let's break that down. It's two ideas smushed together: C-symmetry and P-symmetry. C-symmetry stands for charge conjugation. It just means that if you have a physical process, the same process should be possible with all the particles swapped for their antiparticles. A universe of antimatter should behave exactly like a universe of matter. The laws of physics shouldn't have a preference. CP-symmetry stands for parity. It's about mirror images. It says that if you watch a physical process in a mirror, the mirror image should also be a possible physical process. The laws of physics shouldn't be able to tell the difference between left and right. For a long time, physicists thought both of these symmetries were perfect. But in the 1950s, an experiment led by Qi and Xiongwu showed that P-symmetry was violated. The weak nuclear force, which governs certain types of radioactive decay, could tell the difference between left and right. It was a stunning discovery. The universe at a fundamental level is left-handed in a certain sense. Physicists then thought, okay, maybe P-symmetry is broken, but the combined symmetry CP is still perfect. CP-symmetry means that if you swap all particles with their antiparticles C, A, and D, you look at the process in a mirror P, then the result should be identical. It's like saying the laws governing antimatter are the perfect mirror image of the laws governing matter. But in 1964, another bombshell experiment showed that even this combined CP-symmetry was broken. James Cronin and Val Fitch found that some rare particles called kaons and anti-kaons didn't behave as perfect mirror image twins. They decayed at slightly different rates. It was a tiny effect, but it was real. The laws of physics do have a preference, a slight bias for matter over antimatter. This was a monumental discovery. It was exactly what Sakharov's recipe called for. If a particle and its antiparticle don't behave in exactly the same way, then maybe one can be produced more often than the other. The third and final Sakharov condition is that all of this had to happen at a thermal equilibrium. Thermal equilibrium is a state of perfect boring balance. It's when everything is at the same temperature and energy, and all processes are happening at the same rate forwards and backwards. If the early universe was in perfect thermal equilibrium, any process that created an excess of baryons would have been perfectly balanced by a reverse process that destroyed them. But you'd get nowhere. To lock in an imbalance, you need a period of rapid change. The Big Bang itself provides this. The universe was expanding and cooling at an incredible rate. It was a system violently thrown out of equilibrium. This rapid cooling could allow a temporary imbalance to be frozen in before the universe had a chance to smooth it out again. Imagine a factory making equal numbers of left and right gloves. If the factory suddenly shuts down in the middle of a production run, you might be left with a slight excess of one type of glove. The cooling of the universe was like that sudden shutdown, so we have the recipe. You need to be able to change the baryon count. You need a fundamental bias in the laws of nature. And you need a period of rapid change to make it stick. Now, the hard part begins. What specific physical process actually did this? We have the conditions, but we don't have the culprit. This is where physicists become detectives, looking for a suspect that fits the description. One of the first suspects was right inside our current best theory of particles, the Standard Model. The theory has all the ingredients. It turns out that at the incredibly high temperatures of the early universe, baryon number is not conserved. There's a process called a Sphaleron transition that can convert leptons like electrons into baryons like quarks. So Sakharov's first condition can be met. The Standard Model also contains CP violation. We see it in the behavior of quarks, just like the Cronin and Fitch experiment showed. So, the second condition is there too, and the early universe was definitely out of thermal equilibrium. So, it seems that we have everything we need. This idea is called electroweak baryogenesis. It suggests the imbalance was created during a moment called the electroweak phase transition, when the electromagnetic force and the weak nuclear force split into the two distinct forces we see today. But there's a big problem. When we calculate the amount of CP violation in the Standard Model, it's tiny. It's nowhere near enough to explain the huge imbalance we see. The effect is about 1 billion times too small. It's like finding a suspect who matches the description but is far too weak to have committed the crime. Also, further study of the electroweak phase transition suggests it was probably a smooth crossover and not the violent, out-of-equilibrium event needed to satisfy Sakharov's third condition. So while the idea was good, the standard model by itself just doesn't seem to have the muscle to do the job. The answer must lie somewhere beyond what we currently know. This leads us to more exotic suspects, theories that go beyond the standard model. One class of these are called grand unified theories, or GUTs. These theories propose that at even higher energies than the electroweak transition, the strong, weak, and electromagnetic forces were all united into a single grand force. The GUTs naturally predict new, extremely heavy particles. Let's call them X bosons. The 10th bosons would have been plentiful in the first sliver of a second after the Big Bang. And they would have had a very interesting property. Their decay could violate baryon number conservation. And the 10th boson might decay into two quarks, while its antiparticle, the anti-X boson, might decay into an antiquark and an antilepton. This is exactly the kind of rule-breaking Sakharov called for. Now, add in CP violation. The GUTs could easily contain new sources of this bias. If they did, it would mean the X boson and the anti-X boson would not decay at exactly the same rates. The 10th boson might have a slightly higher chance of decaying into quarks, while the anti-X boson had a slightly lower chance of decaying into antiquarks. As the universe cooled, all the X and anti-X bosons would have decayed away, and if they had this biased decay, they would have left behind a small surplus of quarks over antiquarks. That's our matter. This is a beautiful and compelling story, but it comes with its own problems. The energies required for GUTs are astronomical, far beyond anything we could ever hope to create in a particle accelerator on Earth. The theory is very difficult to test directly. GUTs also make another startling prediction that protons are not truly stable. Over immense timescales, they should decay. Giant experiments have been built to watch for this. Huge vats of ultra-pure water in deep underground mines, surrounded by detectors, just waiting for the flash of light from a single proton giving up the ghost. But after decades of watching, we have seen nothing. Not a single one. This doesn't rule out GUTs entirely, but it puts tight constraints on the simplest versions of them. So the detectives are still searching, and this has led them to what is perhaps the most popular and promising suspect today, a process called leptogenesis. The name gives a clue. Instead of creating the imbalance with baryons quarks first, maybe the imbalance was first created with leptons, electrons, and their cousins, the neutrinos. Neutrinos are strange, ghostly particles. They barely interact with anything. Trillions of them are passing through your body every second, and you don't feel a thing. For a long time, we thought they had no mass, but we now know they do, even if it's incredibly tiny. The standard model can explain why neutrinos have mass. This is another major puzzle. This leptogenesis connects these two great mysteries. The leading theory for why neutrinos have mass is called the seesaw mechanism. It suggests that, in addition to the light neutrinos we see, there must be a corresponding set of super heavy neutrinos that we haven't discovered yet. They are sometimes called sterile neutrinos because they don't interact with the other forces. The leptogenesis idea goes like this. In the very early universe, these super heavy neutrinos would have been created. Just like the X bosons and GUTs, these heavy particles would have decayed as the universe cooled. And their decays could also be biased. They might decay slightly more often into leptons, like electrons and regular neutrinos, than their heavy antineutrino counterparts would decay into antileptons, like positrons and antineutrinos. This would create a universe with a slight excess of leptons over antileptons. So far, this doesn't explain the baryon symmetry. But here's the clever part. Remember those Phaleron processes from the standard model? The ones that were too weak to create the matter excess on their own? It turns out they are very good at one thing, converting a lepton imbalance into a baryon imbalance. At the high temperatures of the early universe, these processes were buzzing, constantly trying to balance the books between leptons and baryons. If you feed them an excess of leptons, they will automatically spit out an excess of baryons to even things out. So leptogenesis is a two-step process. First, the decay of heavy neutrinos creates a surplus of leptons. Then standard, well-understood physics converts that lepton surplus into the baryon surplus we see today. It's elegant, and it's exciting because it links the mystery of our existence to the mystery of neutrino mass. If we can understand one, it might give us the key to understanding the other. This isn't just a story. It's a hypothesis we can test. If leptogenesis is right, it requires that neutrinos and antineutrinos behave differently. It requires CP violation in the lepton sector, and this is something we can actually measure. Around the world, giant experiments are being built to do just that. In Japan, the T2K experiment fires a beam of neutrinos hundreds of kilometers through the Earth to a massive underground detector. In the United States, the Dune experiment will do the same over a much longer distance, sending a beam from Illinois to South Dakota. They are looking for something called neutrino oscillation, the ability of neutrinos to change flavor as they travel. They create a beam of one type of neutrino and see how many have changed into another type by the time they reach the detector. The crucial test is to run the experiment with neutrinos and then run it again with antineutrinos. If leptogenesis and the seesaw mechanism are correct, the rates of oscillation should be slightly different for neutrinos and antineutrinos. This would be a direct observation of the kind of CP violation needed to create a matter-dominated universe. The first hints from these experiments are tantalizing. They suggest there might be a difference, but the data isn't conclusive yet. We need more precision, which is what the next generation of experiments is designed to provide. While some physicists are chasing neutrinos, others are taking a different approach. They are trying to catch antimatter and study it directly. At CERN, in a facility called the Antiproton Decelerator, scientists are performing an incredible feat. They create antiprotons and positrons and carefully bring them together to make atoms of antihydrogen. Then they hold these anti-atoms in powerful magnetic traps, suspending them in a vacuum so they don't touch the walls of the container and annihilate. Experiments like alpha and base are studying these trapped anti-atoms with breathtaking precision. They are measuring things like the energy levels of the positron in an antihydrogen atom or the magnetic moment of an antiproton. And they are comparing these properties to those of regular hydrogen. The goal is to ask a very basic question: is antimatter truly a perfect mirror image of matter? So far, every measurement has shown that it is. Antihydrogen seems to be a perfect reflection of hydrogen. This is what our current theories predict, but it also deepens the mystery. A fundamental theorem of physics, the CPT theorem, says that if you swap charge C, flip in a mirror P, and reverse time T, the laws of physics must remain unchanged. Since we know CP is violated, this implies that T-symmetry must also be violated by a corresponding amount to keep the overall CPT symmetry intact. If an experiment at CERN found even the tiniest difference between hydrogen and antihydrogen, it would mean CPT itself was violated. That would rewrite physics from the ground up and could provide a whole new way of understanding the matter imbalance. But for now, the symmetry holds and the puzzle remains. So where does that leave us? We are stuck with a profound and beautiful problem. We live in a universe that shouldn't exist. Our presence is a constant, glaring exception to what we believe are the fundamental rules of nature. We have a solid set of conditions, a recipe for our own existence, laid out by Sakharov decades ago. We have a list of suspects, from the familiar but underpowered physics of the Standard Model to the grand, unproven ideas of GUTs and the clever two-step scheme of leptogenesis. And we have a plan of attack. We are smashing particles together at the LHC, looking for new sources of CP violation. We are building gigantic detectors to see if neutrinos hold the key. We are building magnetic bottles to hold pieces of anti-reality and see if they have any flaws. We are staring at the faint afterglow of the Big Bang itself, the cosmic microwave background, searching for subtle imprints left by the events that shaped the first moments of time. The answer, when it comes, will be more than just a solution to a difficult problem. It will tell us something fundamental about our place in the cosmos. It will confirm that our universe is not perfectly balanced, that its beauty and complexity arise not from perfect symmetry, but from a tiny essential flaw. The fact that the universe is not empty is the most important data point we have. We are the evidence. Every atom in your body, every star in the sky is a clue. We are the leftovers of a cosmic war between matter and its opposite, a war that matter won by the slimmest of margins. 1,000,000,001 to 1,000,000,000. That one part in 1,000,000,000 is everything. It is the difference between a universe full of light and a universe full of life. It's the reason we are here, able to wonder about it all. The investigation continues.